Hello, I'm Julian Dolby from IBM Research. Thank you for inviting me to SCAM this year, where I want to tell you about Walla, Taint, and the IDE using Zhennu taint analysis. In Chinese legend, Zhennu is a weaver goddess, and our taint analysis is going to weave together a variety of languages and IDEs and Walla analyses to build a comprehensive taint analysis. Also in Chinese legend, Zhennu, the weaver goddess, was a user of the Magpie Bridge, and our software will make use of Magpie Bridge as well. Now, the purpose of this analysis is what I'm going to call deep integration with the IDE. So we're going to have, we have to provide powerful analysis with things like context sensitivity. After all, that is what Walla does. But once you have the analysis, you want to provide customized information display when the analysis is likely to compute some kind of artifacts about your code, and you would like to show them in the most natural way possible, not necessarily cramming them into a hover or something like that. So we need to be very flexible in terms of the displays, the IDE integration that we support. And on top of that, Walla supports multiple languages, and we need to make sure that our IDE integration supports multiple languages as well. And there are many popular tools out there, and we need to make sure we can support all of those as well. So to give you a sense of what we've been doing, let me show you an example with Zhennu taint analysis running on JavaScript in Eclipse Che, which is the Kubernetes native IDE for developer teams. So let's just look at what we do here. The first thing, we bring up a piece of JavaScript code, and let me just pause for a moment. If we look at this piece of code, all it's doing is it reads document URL in a couple of places, so that would be a potentially vulnerable piece of information, right? That the URL is often can be subject to manipulation sometimes. And then ultimately you can see that that's passed through this ID method, and ultimately it flows back into the text field there, and then ultimately to document.write. So we would expect to see a few tainted flows. Then the analysis does indeed produce the tainted flows, and you can see the elements of the tainted flows are highlighted with underscores there. But we also have something called, we have witnesses, and a witness being a trace, a flow that illustrates tainted data. So let's just bring up one of those, and we can see, so we can see the flow. It starts at document.url, as you'd expect, and so let's just click on document.url there. Okay, so there's the highlighted one. Then it goes to document the ID call. Now the call goes to ID returns X. We then return from call, and that ultimately flows to document.write. So that's one of the flows that we have. But we had another one here, and how does that one work? It should be similar, since again we have sources, and the source and sink will be the same ones. In this case, it's a document.url. It's indeed, again, the source, but in this case, it's a different one. It's the one there on line 15. That then flows to an id3.id, which again calls ID as before. So that shows ID, and then ID returns its argument, returns from the function, and again, it's assigned to the text field and goes to document.write. So this is what I mean by deep integration. So in this case, the tainted flow really looks very much like a graph. So what we wanted to do is actually display it as a graph. Now, graphs are not native to Eclipse Che or most other IDEs, and so we need a way to integrate our graph display into Eclipse Che and everything else in a way that looks relatively seamless like this. Now let me just make clear that this is not something that we're doing for Eclipse Che. Let's look, or for JavaScript. Let's just look at the next thing. Here we have a Python piece of code. It's written in PyCharm. Again, this is a Flask application, and basically what it's doing is it's tracking tainted data flow from there on line 16. You request.form suggestion. It's then passed through that outer inner call there on line 20, and it's then passed a subprocess.call, which is a place where data escapes to the outside world and hence is a tainted sink. Note in this case that there's another subprocess called there on line 18, but and the analysis needs to make sure that we understand that, well, 21 is actually getting tainted data, 18 isn't, since the argument it gets is a self-isolating string, which means we need enough context sensitivity to handle the data flow through outer and inner without being confused. So, some analysis challenges there. But we can go further. This is Java in code. Voila does Java, of course, and in this case, this is an Android Studio. So we're looking at Java Android code. So in this case, we have a similar tainted flow. We have this SMS manager.send text message. That's a place where data escapes to the outside world. And a source, we have those get device ID. So basically, we're getting the device ID. We are then, and you can see from the graph, we are then returning it from the function f. We are then returning from method there on line 38, and that part is called passed to SMS manager.send text message. So you can see quite precisely what the flow looks like there in our graph. And again, this is a graph of Java code, and it has to understand Android, and you need enough type analysis and data flow to understand the call, to resolve the call to test1.method correctly and have it go there to test and then call B, and rather than going to A. So there's again some analysis challenges there. And for one more example, I want to show you HTML. In this, Voila, in addition to analyzing JavaScript, also analyzes HTML, by which we mean we take an HTML file, we extract the JavaScript, and we build a model of the DOM to the HTML, and we analyze the whole thing together. And in this case, I'm showing it in VS Code. And so here you can see the piece of code, the JavaScript code is very similar to the examples that you saw in Eclipse Che, but it's embedded in an HTML context, so we have to understand that there are multiple script tags, and we need to understand the way the data flows between those. And in this case, again, the source is the same. Somebody has highlighted the source there with the box document.url. That then goes to id.call, and then that passes through the ID method there on line 6. So that's just like the JavaScript code you saw before, but it's in HTML. And this is now in VS Code. So this is the kind of thing we want to now notice that what I've been doing there, I've been using the same taint analysis on different languages. And the display there, the graph, is similar, but on the other hand, it's integrated differently into each of multiple IDEs. So we're not, this is what we mean. We need deep integration, but we need deep integration across a range of IDEs. So this is kind of a large space. We have lots of IDEs. You've seen Eclipse Che, PyCharm, Android Studio, VS Code, and there are many others. And you've seen 4 different languages: Java, Python, HTML, and JavaScript. There are other languages. These are the ones that Voila focuses on now. And you saw at least some hinting at the analysis challenges which we address with things like static single assignment form, IFDS, the system dependence graph. So we have a significant piece of analysis infrastructure for these different languages and for all the IDEs. We aren't surely going to create infrastructure, all of this infrastructure separately, and we won't. Voila is a cross-language, and which is one thing we use, and GNU is going to weave together the cross-language capabilities of Voila, the integration of Magpie Bridge to produce a comprehensive taint analysis. GNU, in some sense, is going to weave it all together. Now, we are going to start by talking about Voila, which is probably a review for some of you. Voila is an analysis infrastructure across multiple languages: Java, Python, HTML, and JavaScript. And the way it works is by not building front ends, but using existing front ends and building something we call the Common Abstract Syntax Tree, or CAST, from those. We use JDT for Java, we use Jython 3 for Python, we use Jericho for HTML, and we use Rhino for JavaScript. For each of those, we extract some form of somewhat analyzed AST, and we build our own Common Abstract Syntax Tree from that. From the Common Abstract Syntax Tree, that's from where we generate our internal representation, which is based on the control flow graph, static single assignment, and is basically a fairly traditional compiler IR. And from that IR, that is all we build things like IFDS, call graph construction, data flow analysis, program dependence graphs, systems dependence graphs, and the like. And all of that is built on top of a rich library of support structures, including things like bit vectors, data flow solvers, and graphs. And all of that, of course, is available on Walla, the Walla site. Now, to give you a flavor of how we use some of this stuff, let's start with the core of how GNU does taint analysis, which is graph reachability. Now, we start with simply a graph. That's a Walla abstraction. It's just a graph of something. And what we are going to do, we take one other thing. We need an endpoint finder. And the endpoint finder called sources, what it's going to do is for any node in the graph, it's just going to tell us true if it's a source of tainted data, and false if it isn't. So basically, we iterate across all the nodes in the graph there with the orange highlight, and then for each statement, we check whether or not it's a source of taint. If it is, we create a path finder. That's a Walla utility for constructing shortest paths through a graph. And we construct paths to sinks. So we also take a sink endpoint finder, which is sort of like the source one, except it returns true for sinks, places where tainted data isn't supposed to go. And so now our paths are looking for each source, we are now looking for any flow to a sink of tainted data. So that is all of the things that the paths we would like to find. Once we find those paths, we gather them up into a list and return that. But if we do that, we need something on which to call graph reachability. We need a graph. So what we're doing, this is a top-level piece of analysis code. In this case, it would be called by Magpie Bridge in this case. It's given a bunch of source code and told to analyze it. So the first thing we do is we create an AST SSA propagation call graph builder. This is Walla's abstract class that represents call graph construction and pointer analysis across all the languages supported by Walla. And we have this make builder abstract function whose job is to create a builder for the appropriate language. Clearly, you need different builders for Java, JavaScript, Python, and HTML. So once we have a builder, we then get the call graph. There's CG, and then once we have the call graph, we create the SDG, the system dependence graph, which is essentially a whole program data flow graph built context sensitively using IFDS. And that's one. And then once we have that graph, we use that for getting the paths. Once we have that graph, we'll then look for all the tainted flows through the SDG. And we'll come back shortly to what we do with the paths. But for now, let's look at the components, because we have to build some stuff, right? We had this source finder and we had this sink finder. And we're just going to look at the JavaScript ones. There are analogous components for the other languages. So in particular, let's look at the source finder. We're looking for normal statements. We're looking for statements. In fact, we're looking for get statements. Those are field reads. And we are looking for field reads that read the field URL. If you recall from our example, the tainted data flows all started in the document.url call, and that's what we're illustrating here. And on the other hand, we have sinks. That's the other end of the path. And in particular, in this case, remember there was the sink finder. And in this case, if you remember from the code, the data all went to document.write. So what we are looking for is calls, so the arguments to calls, and this is a param callee, that's the Walla notation for that. And when we have one of those, we say what method is it, and is it the document prototype write method? That is Walla's model for document.write. And if it is, then we collect those up. So now we have the sources and the sinks that we can give to the Pathfinder. And you may recall the other piece of code there that was in the top was this modref. Modref is an idiom for dealing with heap reads and writes, and that's slightly specialized per programming language. It's mostly generic, but there's a little bit of specialization. And in this case, we're creating one particularly for JavaScript. So those are the components of how we are going to use Walla for analyzing our JavaScript. But that's part of what we want. So now we have the results, and remember we saw that get paths call. What are we going to do with the paths that we get? So what we need to do is somehow show them in the IDE, the way you saw in Eclipse Che and the others. So Magpie Bridge supports LSP and HTTP. We have added two small extensions to LSP. We have something called show HTML, and what that does is it instructs the IDE to show HTML in a web view integrated into the IDE somehow. That's one piece. The other piece, if you remember people clicking on links, the other piece is an extension we have called jump to, which you give it a position and it highlights that position in the code, as you saw with those white boxes in Eclipse Che. So to illustrate a little bit of how that works, and these are relatively lightweight, so the implementation of both of these features in VS Code is roughly 50 lines of code, and it's all on the outside. There's no messing with anything. Just to illustrate how it works concretely, you saw this is a screenshot from Eclipse Che again. In this case, so you saw the witnesses before. So what happens is with LSP, the LSP will tell you Walla will compute that there's a witness, and then the show HTML extension is going to allow us to bring up our graph inside the IDE, inside Eclipse Che, and then inside the graph, the nodes are all clickable. And when you click on it, it ultimately calls jump to highlight the appropriate piece of code in the IDE. So to give you a little more detail, what happens is the first step is to make a witness trace. So you remember we said paths. So when we edited the driver, we did computed paths. Now this is what we do with them. For each path, we are going to go through, and you don't need to read the code in detail, but the first step is to create a viz.js graph data structure. Which is basically the nodes and edges. And notice that we have precise information of Walla. We can get positions, we can get source text. So we can take the IR nodes that constitute the tainted path, and we can extract all the relevant source information to make viz.js graph data. Then we now have HTML to show the graph in this GNU web API call. And to do that, we build the command. Remember, you saw witness in the we clicked on witness in the Eclipse Che demo. That's where this comes from. This is a command. We said it's titled to witness, which is the thing you saw, and its job is to open the URL. It opens this GNU call, and then the result has the witnesses, as you saw and how that worked. So once we do that, there's one other piece that we need, which is the visualization using the using Viz.js. So Viz.js has the ability to add actions. So what we do is we've created this select node call, which will call back, which will be called anytime a user clicks on a node. And what it does is it gets hold of the information that we built in, that we passed from the code, which is the source positions and text and things. And then it calls this jump web API, which will then cause Magpie Bridge to go back and call jump to, which is what you saw in the demo and the slide. So that's all I have to tell you today. So thank you for listening, and I would encourage you to look at all of the pieces of this in Walla, in the example, the GNU example, and of course in Magpie Bridge as well. So with that, thank you very much.